Hello everyone, we are here in another weekly live that happens every Tuesday at 10 p.m. London time. And as you could see, the last weekly lives, we focused on the main data structures. And today we're going to be talking about the queue data structure. It's a very important data structure we use for important algorithms such as breadth first search. We're going to be exploring some of them as well today, and we're going to be exploring what are the main concepts of a queue. So by doing coding interviews, we're going to have to use queues, and well, even though we don't use queues very much in our day-to-day jobs, are very important in coding interviews, in algorithms, and that's the main reason we're going to be exploring the main concepts of a queue. But even if you don't use them for coding interviews, it's still a very good skill to have, a very good knowledge to have, because this is the foundation of programming, right? So let's take a look then what are the main concepts of a queue. So the definition of a queue is basically a real queue in the real world, right? So imagine people in a bank for a queue to pay a bill in a bank. So the first to be attended will be the first to get out. First in, first out. It's the same concept of a real queue in the real world, right? But use cases in the programming world could be scenarios like scheduling tasks, handling asynchronous data, or breadth first search algorithms. So have some use cases. And what are the basic operations of a queue? So the first one is to enqueue data, which means to add an item, add an element to the back of the queue. Dequeue, remove an item, remove an element from the front of the queue. Pick is just to get the item at the front of the queue without removing it, right? And the is empty, that will basically check if the queue is empty or not, and size, where we get the size of the queue. And what are the types of queue? So simple queue uses a regular FIFO model, first in, first out. There is a circular queue, which enhances the simple queue by connecting the end back to the beginning. So this would make the queue more optimal for storage. We also have PriorityQueue, and we're going to see it in code, how it works in Java. So basically, those elements, they have a number we give, or a weight. We could also say as a weight. And depending on the number we give to those queue elements, they're going to be prioritized or ordered in a different way, right? We also have the double-ended queue, which is the Deque, which allows insertion and removal of elements from both the front and the back. So those are some basic fundamentals of queue. And obviously we have the implementations of those fundamentals in Java, right? So we have those fundamentals implemented in the Java collection framework. So what are them? So first we have the queue interface. And what are the characteristics of the queue interface? So we're going to, basically it represents the FIFO queue, right? The first in, first out. And the methods are add, offer, remove, pull, element, and pick. And the implementations of queue are linked list. So if you see behind the scenes, a linked list is composed by nodes. And you're going to see that a linked list also implements a queue. And a linked list is good for implementing a simple queue. ArrayDeque is a resizable array implementation of the Deque interface. It's more efficient than linked list when used as a queue. So for most operations, ArrayDeque is recommended to use because it's a lot more optimized than linked list for most cases. We won't see all the details about those collections, but at least remembering the key points is what matters. for interviews and even for day-to-day work, because you don't really need to know all the details of those implementations. And for PriorityQueue, it implements a priority queue based on a priority heap. So I'm gonna show you in practice how this collection work, and the elements will be ordered by their natural ordering. So whatever is implementation of the comparable method, we're gonna see the elements ordered by the rule of the compare to method. I'm gonna show you how it works in code and what are the practical considerations. So capacity issues, some implementations like ArrayDeque have capacity restrictions. So if we need to add lots of elements, it's better to use a linked list, because ArrayDeque actually is an array behind the scenes. It's not chained node as a linked list. And for thread safety, most queue implementations like LinkedList and PriorityQueue are not thread safe. So if you want to use a queue that's thread safe, then you can use the ConcurrentLinkedQueue, right? And we also don't have a capacity constraint here, because a linked list is just a chain of node objects. So obviously a chain of node objects will occupy more memory, right? Because we are chaining objects. And here on the ArrayDeque, we occupy a lot less memory because it's an array behind the scenes, right? So, and regarding performance, different implementations have different performance when we do insertion, removal, or traversal, and some comparison and choice. So the criteria here depends on factors like performance needs, capacity, thread safety, and whether the queue needs to handle priorities. So obviously, if we need to handle priorities, we have the PriorityQueue. It's a very obvious choice, right? And so let's see some examples here of decisions. So we have the linked list for simple first in, first out queue with no capacity constraints. Why is that? It's because we can chain node objects, as many node objects as we want, right? But if we want high performance and non-concurrent simple queues, we can use ArrayDeque. And obviously, if we need priority, if we need some kind of priority in our queues, then we use the PriorityQueue collection, right? And basically, it's not very complicated, as you can see. Like the concept of a queue is basically the same as we have in the real world, right? It's first in, first out. So let's see now some examples with code so that you see some of the most common algorithms it would use with queues. So let's see here. Okay, so let's go to the queue time complexity. That's very important. So first, let's see the linked list. So we have this method. So what are the main characteristics of the linked list? So the linked list implements queue and Dequeue interfaces. It has the methods pull, offer, pick. All of those methods are all one. Also, if you see a linked list, it's a doubly linked list. It works as a stack and queue. The advantages are that, like, because it's a connection of nodes, it has dynamic size. Like, you don't need to create a new array when the array is full because it's dynamic, right? It's just a connection, a chaining of node objects. So it's efficient for insertions and removals at both ends. Disadvantages are that we use more memory than array-based queues because it's lots of objects, right? We're going to have to create lots of nodes. So when it's best to use a linked list is when we frequently add or remove elements from both ends. So regarding performance, like we have, like for adding and removing, those are fast operations, but it's usually recommended to use ArrayDeque because linked list is slower than ArrayDeque for the vast majority of operations. So an implementation, like I said, is with nodes, with previous and next pointers, and there's no thread safety. So if we see here the linked list, you see that it implements list, Dequeue, And Dequeue extends queue, right? So linked list is a double-ended queue. It's a queue as well. And as you can see, a linked list behind the scenes is actually a chain of objects, right? You can see the node, the generic type, E here, whatever you can pass any type you want. And yeah, those are important details to remember about linked list. So let's go back here, the code. All of those methods are O1. So we are basically adding an element to the end of the linked list. Here we just pick the first element, the element that is in the head of the collection. Poll removes and returns the head element. And here return the size. And this method is the is empty. Like you see here, it's a very simple method. So it's just you just compare if the variable size is equals to 0. And then after linked list, we have the ArrayDeque. So what is the ArrayDeque? So it implements the queue with O1 amortized time for all queue operations. It's based on resizable circular array implementation. It's more memory efficient than linked list because we don't have node overhead. It's actually an array behind the scenes, right? So we have better performance due to improved cache locality. It can function as last in, first out, as LIFO, as also known as stack, or first in, first out, which is a queue. It's not thread safe, so like we have to use concurrency wrappers if needed. Cannot contain no elements. It's faster than stack and linked list for most operations. Automatically resizes when capacity is reached. So when the array reaches the capacity, then another array with the double of the capacity will be created and all the elements will be copied to the new array. There is no support for random access or indexed operations. So even though it's an array behind the scenes, it keeps the contract of a queue, right? And maintains head and tail indices for efficient operations at both ends. And it's also the recommended choice for stack and queue implementations. So let's check here how is the ArrayDeque behind the scenes. So as you can see here, firstly, it's an array. So these elements, and as you can see here also in the Java doc, it says here, this class is likely to be faster than stack when used as a stack and faster than linked list when used as a queue. So there are some advantages of using ArrayDeque. And as you can see, ArrayDeque is actually behind the scenes an object, but we can't access those elements by indexes because this would break the contract of a Deque or a queue, right? So obviously we won't explore the whole class here because there is a lot to cover, but I just wanted to show you that behind the scenes, an ArrayDeque is actually an array that implements all the operations of a Deque, right? So let's go back to the code, to the example. So the offer method is O1, is the same. It's all O1. Pick, poll, size, and is empty is all O1. And we also have the PriorityQueue. And this queue is obviously priority-based queue implementation, not first in, first out. Elements are ordered by natural ordering or custom comparator. So the elements will be ordered depending on the implementation of our two method. So in this case, we are using the integer wrapper class. So if you see here, the integer, we have the compare2 method, right? So we have this compare2 method, and whatever we have implemented in this compare2 method will be executed in the PriorityQueue, right? Let's see. So in this case, we are inserting 30, 10, and 20, and we have some methods here. We have the same peak, we have pull, and this is O log n because the PriorityQueue will basically remove the mean element and we'll restore the heap. And to get the size, it's O1 because it would just get the size variable. Okay, and let's have a quick look in the PriorityQueue class. So it's an array of objects here. Here we can see the comparator. Basically, the elements will be ordered in whatever is the implementation of the object here. And we also have the ConcurrentLinkedQueue. And why would you use that? Because it's thread safe, non-blocking queue using the Michael-Scott algorithm. It's high performance implementation using compare and swap. It's O1 time complexity for the offer, pull, and pick methods. It has also unbounded capacity with no blocking behavior. It has higher throughput than synchronized collections for current access. And we have no constant time size because it requires full traversal. Cannot contain null elements. It's obviously suitable when you are working in a multi-thread environment. And it has lower latency than lock-based alternatives. So here in this case, you have the offer method, which is O1. We have the pick method that we get the head element. It's also O1. The poll method, we remove and return the head element. And this size method, we have to traverse the entire queue. So let's explore here what's going on. Yeah, so it's because it's asynchronous. So we need to iterate all the elements here. The syntax is a bit weird, but it's basically an infinite looping. So very interesting. Okay, so we also have the LinkedBlockingQueue. So it's a thread safe first in, first out that blocks when full or empty. We have the two lock design which separate the head and tail, and it also enables us higher throughput. So we have O1 for operations, including accurate size method. It's ideal for producer consumer patterns with blocking semantics. So it has O1 for all the operations. Right, so all these methods here during two that will basically remove elements from one collection and put that in the other collection, right? So let's run all of those methods now, and we can see what's going on. Blocking queue, ConcurrentLinkedQueue. On the PriorityQueue here, you can see that the elements were ordered, right? And the others are pretty much the same. Okay, so let's continue. This is the generate binary numbers. So let's debug it. So basically, we're going to generate the binary numbers from 1 to 10. So let's continue here. And the queue data structure works very well here. So let's see. Yeah, okay, great. So let's see here the result. Yeah, it's actually from 0 that we generate the binary code. So let's see here the output. This is the output from this algorithm. So let's continue then. And basically in this algorithm, we're going to be traversing nodes, right? So this is very interesting because then we can understand better how a linked list actually works behind the scenes. So let's go here. We put a tree node on the, then we create more object references for the left pointer and right pointer. And then we go from the left point left. So basically it's a reference of a reference, right? And basically, if you notice here, that's what we are doing, right? So this is tree node root, which is 1. And then on the left, we put the tree node 2. On the right, we put tree node 3. And then from this left pointer, we get the left pointer, right? And then we insert 4. Then from left, right, we insert 5. And from right, we insert 6. Okay, so let's continue. So basically in this tree node, we have all the other nodes. Okay, so let's see here. So as you can see here, we have the reference left, right? So we can see other references here. So let's continue. And here we are using basically the breadth first search algorithm. So we remove the first element here, the current level. Let's continue. So in the result, we have exactly what we were expecting here, right? So 4, 5, 6, 2, 3, and 1 as a root. So level 0, we have 1. Level 1, we have 2, 3. And level 2, we have 4, 5, 6, right? Okay, let's see the other one. Queue using 2 stacks. So let's debug it. So we have the stack 2, and we check if it's empty or not. So let's check how the methods work here. So this method, Dequeue, will basically remove the element from the queue. So basically, if stack 2 is empty, you're going to transfer all the elements from stack 1. For the pick method, so we would check if stack 1 is empty, and then the stack 2, we push the elements that we're going to remove here on this pop method. So the pop method returns at the top of the stack, right? And it's going to also remove the element, the size of 3. And finally, we have this algorithm here, stack using queues. It is also a bit complicated. So we use Q1 and Q2. We instantiate using LinkedList. So, and then we have to use some queue methods here, one to add, another to remove. And yeah, I recommend you to debug this code later because it's also, I don't have much time to explain all of them here. And I'm going to have another meeting in a few minutes. But I will pass the code to you, and then you can debug this code, and you can learn a lot more about queues. But the most important thing about queues is to remember when you should use them. The BFS algorithm is also very important. So those are the key elements of this algorithm. I recommend you to debug all of those data structures from this code and just make it second nature for you. That's pretty much it. So the next weekly live, we're going to be talking about stack. So I'm going to come up with 5 algorithms also that we see a lot in coding interviews using stacks. We might explore a little bit of recursion because behind the scenes, recursion uses the stack data structure as well. So we're going to be exploring that. And that's pretty much it. So thank you so much for being here. And I hope to see you next Tuesday at 10 p.m. London time here. Okay? So I'll see you and I wish you a great week ahead. Cheers.